So I will speak today about process development using DynoChem. I focused on particular step of hydrogenation step. So discussion topics today, I will say something about model-based approach to the process development. We can basically look to the DynoChem as some big calculator. So this sentence, virtual process development, is something what is written inside this pharma paper here, supplying the future. Which path will you take? You will during this approach, you are faced with different kind of challenges, from chemical development to the engineering development up to production scale. So all these different aspects needs to be considered during process development. All these initiatives can be found in the ICH guidelines from Q8 to Q11, and the basic this fundamentally approach means that you need to have some kind of process understanding. And process understanding means that you will need to obtain the required knowledge to allow predictions on different scales. So if we had additional solid phase, we will have another equilibrium, so we will have a mass transfer between solid and liquid phase at the same time. But in our case, we have heterogeneous reaction, and we were only in our catalyst is dissolved. So we had problem only by gas-liquid mass transfer. After that, we use experiments to fit all these constants. We use a lot of constants to fit, as you can see previously on model or of mechanistic model we use in our work. This work is presented in the paper. You can what you can find here on this slide over here. So you can see the change of starting material to product on the left, A picture, and on the B picture you can see impurity formation. So even from this parameter point of view, the temperature is really important. So we try to push temperature as high as possible. So pressure is also really important. We try to push also hydrogen as high as possible. It's just common thing. But safety consideration during scale up, we could not go at such a high temperature. So we try to be something which can be obtained in a production scale. Our safety departments told us that 6 bar is something which is something comfortable, so we try to use this 6 bar for scale up. And also amount of catalyst, you can also use as high as possible catalyst, but you need to consider something what is optimal, and we found that 1 mole% is something which we can work with. And you can also show these results by plotting. I use this 2-dimensional plot because it's quite hard to see. We all live in 3-dimensional space. And you can see the response surface analysis if you look at the different pressure and amount of catalyst, and if you change the KLA constants and temperature, and you can see these response. Basically, you want to find yourself in the yield as high as possible and impurity as low as possible. And if you really have these response surface plots, you can basically design your process, and you can have some kind of idea of control strategy of your process. So next step is to define which parameters will I allow for production to have in order to control process. So we use this on scale up on 40 liters, 40 liter scale. We allowed a certain range of process parameters, and we use different steps, different batches to really validate this model. And this is the final scale up on the production scale. The slight changes because we measure these points on the picture over here dry mass, because on GMP production you are not able to take samples from reaction mixture. So we consider still a pretty good agreement between theoretical values and values predicted by model. So we also see no decrease of activity and anti or chemoselectivity, and we have good impurity levels within the expected range. And of course, I will give some kind of conclusion. So at least I hope that I show you that computer-aided process design could be really useful. DynoChem is really show that it is really powerful tool, and Teva recognize this added value of process simulation tool. I also need to say my gratitude to some of my colleagues from Teva, especially Amr Gold, which push the DynoChem in Teva these last couple of years. And the guys from production and from chemistry also realized that DynoChem is really powerful tools which can help us from different kind of aspects. So I also show you that systematical pharmaceutical approach to the process development could be also really useful if you begin with predefined objectives, if you define specification and you allow the process space within which is allowed, and you will be able to control your process. I showed that on the case of primary amine hydrogenation. So final conclusion that you will be able to scale up your process from different scale, from lab up to pilot plant and up to production. And this mechanistic approach is really useful to obtain in-depth process knowledge, and you will be able to control process impurities. And of course, you will be enabled to optimize your process and late phase interventions.